Continuing with coupling in proton NMR, here is the low resolution spectrum for this molecule, so before coupling. The two red hydrogens give this peak, and the green hydrogen gives this other peak. I'm going to put markers on for the original shifts, and then imagine that one of the red hydrogens is spin up, which will cause one of the green hydrogens will be affected by this and move to a slightly higher chemical shift. In fact, there are actually two red hydrogens, so they could both be spin up, and this would mean that the green experiences more magnetic influence and is moved slightly higher upfield. Alternatively, both of those red hydrogens could be down, and so that would mean that the green hydrogen would feel less magnetic influence, and so we'd see a peak shifted to a lower chemical shift. There are two combinations of being one spin up, one spin down, and so therefore we'd get a superimposed peak on the original chemical shift. And the same thing can occur in reverse. The green hydrogen could be spin up, which will cause the red peak to move up slightly, or it could be spin down, which will cause that red peak to move down slightly. So starting from the original uncoupled spectrum, after coupling, we see the red's been split into a doublet by the one neighbouring green hydrogen, and the green peak's been split into a triplet by the two neighbouring hydrogen atoms. And this gives rise to, if you like, the n+1 rule. So that's stating that the number of lines a peak is split into is the number of hydrogens on neighbouring carbon atoms plus 1. So for the green hydrogen, there are two hydrogen atoms on the neighbouring carbon, and therefore the green peak is split into 3, into a triplet. And for the red hydrogens, there was only one hydrogen on the neighbouring carbon, the green one, and so this red line is split into a doublet. The effect can continue so that you can have quartets with 3 hydrogens on neighbouring carbons, or quintets, or even more. Next, I'll go through some examples of NMR spectra.